March 17th, 1943. North Atlantic, 58 degrees north, 23 degrees west. The SS Richard Hovey wallowed in 12-foot swells, her cargo of Sherman tanks and aviation fuel making her ride low in water that temperature gauges measured at 38 degrees Fahrenheit. At 1400 hours, sonar operator Michael Chen detected propeller signatures at bearing 270, range 3,000 yards. Before the alarm could sound, torpedo tracks appeared in the grey water. The first torpedo struck amidships, below the waterline near frame 62. The explosion tore a hole 15 feet across through quarter-inch steel plating that had been welded in a Portland shipyard just 11 weeks earlier. Seawater flooded 3 cargo holds at a rate that engineering calculations suggested should sink the vessel within 8 minutes. The Richard Hovey remained afloat for 6 hours, allowing crew evacuation and partial cargo salvage. In a cluttered engineering office at the Maritime Commission headquarters in Washington, William Francis Gibbs studied casualty reports from convoy SC-121 with the methodical attention he brought to stress calculations and hull design specifications. The Richard Hovey represented the 43rd Liberty ship to survive torpedo damage that conventional naval architecture suggested should prove immediately fatal. The pattern defied theoretical predictions about structural failure and flooding dynamics. Gibbs had designed these vessels with redundancies that other marine architects considered wasteful, excess capacity that added construction costs without apparent benefit. Critics called his approach over-engineered, pointing to weight penalties and material consumption that seemed irrational under wartime resource constraints. But the casualty reports told a different story. Ships that should sink in minutes were remaining afloat long enough for crew rescue and sometimes salvage. The morning briefing, at Kaiser Shipyard No. 2 in Richmond, California, began at 0600, recorded in production logs that documented welding schedules and steel plate inventory. Henry Kaiser's revolutionary construction methods had reduced Liberty shipbuilding time from 245 days to 42 days through prefabrication and assembly line techniques. But speed created quality concerns that traditional shipbuilders viewed with professional alarm. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Welding supervisor Raymond Torres walked the construction bay where hull section 17 of the SS Robert E. Peary was taking shape. Each Liberty ship required 2,500 tons of steel plate, welded rather than riveted in a departure from traditional shipbuilding that made maritime unions nervous. The welding technique allowed rapid construction but created stress, points that conventional riveting absorbed through mechanical flexibility. Torres checked weld quality with visual inspection and hammer tests that detected subsurface flaws through sound characteristics. His reports noted occasional cold cracks in structural members where thermal contraction created microscopic failures. These defects appeared in approximately 8% of hull welds, requiring grinding and re-welding that slowed production schedules. Quality control represented constant tension between speed and reliability. Kaiser's contracts with the Maritime Commission specified delivery dates that required completing one ship every 3 days across all West Coast yards. Traditional marine architecture emphasized craftsmanship over velocity, an approach incompatible with wartime production demands. The compromise involved accepting minor imperfections while maintaining structural integrity through redundant systems. Engineering specifications for the EC2-SC1 design, the formal designation for Liberty ships, included features that puzzled experienced shipwrights. Gibbs had specified duplicate pumping systems, redundant electrical generation, and compartmentalization that exceeded standard merchant vessel requirements. The additional systems added approximately 200 tons to ship displacement, reducing cargo capacity and increasing construction complexity. Naval architect Thomas Morrison reviewed Gibbs' specifications with professional skepticism during a Maritime Commission design conference in January 1942. The redundancy seems excessive for merchant vessels operating under naval escort, he observed, indicating blueprints that showed parallel systems for critical functions. We're adding weight and cost for capabilities that standard designs provide adequately. Gibbs responded with the measured tone of someone whose calculations accounted for variables that conventional analysis overlooked. Merchant vessels in wartime face damage, scenarios that peacetime specifications don't address, he said, spreading structural diagrams across the conference table. A single torpedo hit shouldn't represent automatic vessel loss if engineering design can provide survival margins. The discussion reflected fundamental differences in design philosophy. Traditional merchant ship construction optimized for cargo capacity and operational efficiency under normal conditions. Gibbs's approach anticipated catastrophic damage and prioritized survivability through system redundancy that seemed wasteful until vessels encountered combat conditions. September 1942, Mid-Atlantic convoy routes. The Battle of the Atlantic had entered its most lethal phase, with German U-boats sinking Allied merchant shipping faster than shipyards could replace losses. Admiral Karl Donitz's Wolfpack tactics concentrated submarine attacks against convoy formations, overwhelming escort vessels, and creating target-rich environments for torpedo attacks. Liberty ships represented essential elements in the Allied logistics chain, transporting military equipment, fuel, and supplies across submarine-infested waters. Each vessel lost meant not just material destruction, but potential strategic impact on operations in North Africa and the Mediterranean. Survival rates directly affected whether Allied forces could sustain operations against Axis positions. Captain Ernest Anderson commanded the SS Stephen Hopkins during convoy TM-1's transit from Cape Town to Paramaribo. His vessel carried war materials including trucks, ammunition, and aircraft components. On September 27th, approximately 700 miles off the coast of West Africa, the Hopkins encountered German surface raiders Stier and Tannenfels. The engagement that followed demonstrated Liberty ship capabilities under conditions their designers had never specifically anticipated. The Hopkins mounted a single 4-inch stern gun and 2 machine guns, armament intended for submarine defense rather than surface combat. Against 2 armed merchant raiders with superior firepower, conventional naval tactics suggested immediate surrender. Anderson chose engagement, maneuvering to bring his stern gun to bear while German vessels opened fire at 4,000 yards. The exchange lasted 20 minutes, during which the Hopkins absorbed multiple hits from German cannon fire. One shell penetrated the engine room, killing several crew members and damaging steam systems that should have disabled propulsion. Redundant pumping systems maintained boiler water levels despite flooding that conventional single-system designs couldn't have survived. The Hopkins continued maneuvering and returning fire until ammunition, exhaustion, and accumulated damage forced abandonment. The vessel sank approximately 5 hours after the initial engagement, allowing crew evacuation that saved most survivors. German raider Stier suffered damage during the exchange that proved fatal despite her larger size and naval construction. She sank the following morning, demonstrating that merchant vessels designed with combat survivability could inflict meaningful damage on purpose-built warships. The engagement entered maritime history as the only instance of a Liberty ship sinking an enemy warship in surface combat. Maritime Commission analysts studied the Hopkins engagement reports with attention to damage control and vessel survivability under extreme conditions. The redundant systems that critics had called over-engineered had allowed continued operations despite hits that should have immediately disabled the vessel. The case validated Gibbs's design philosophy in ways that theoretical analysis couldn't demonstrate. January through June 1943, North Atlantic shipping lanes. Convoy battles between Allied merchant vessels and German U-boats created natural experiments in ship survivability under combat damage. Liberty ships, equipped with redundant systems, demonstrated survival characteristics that differed measurably from traditional merchant vessel designs when subjected to torpedo attacks. The SS Jeremiah O'Brien survived a torpedo hit during convoy HX 235's crossing, remaining afloat long enough for towing to Iceland despite flooding that filled 2 cargo holds. Post-damage assessment revealed that compartmentalization prevented progressive flooding, while backup electrical generation maintained pumping capacity after primary systems sustained damage. Engineering analysis documented the specific mechanisms through which redundancy translated into survivability. When torpedo explosions destroyed primary pumping equipment, secondary systems located in protected compartments continued operation. When main electrical generators failed, emergency generators in separate locations maintained power for damage control and communication systems. The mathematical relationship between system redundancy and survival probability became apparent through accumulated casualty data. Liberty ships showed approximately 35% higher survival rates following torpedo hits compared to conventional merchant vessels of similar size. The improvement represented the direct consequence of design features that critics had considered wasteful. William Francis Gibbs received these reports in his Washington office with quiet satisfaction. The Hungarian-born marine architect had spent his career advocating for scientific approaches to ship design that prioritized survivability through redundant systems and careful compartmentalization. The wartime casualty data vindicated methods that peacetime economic constraints had often prevented implementing. His design philosophy reflected lessons from the Titanic disaster, where inadequate compartmentalization had allowed progressive flooding to overcome vessel buoyancy. Liberty ships incorporated 15 watertight bulkheads that divided the hull into 16 separate compartments. Damage to any 3 adjacent compartments could theoretically be survived, providing margins that conventional merchant vessels lacked. The redundant pumping systems represented another departure from standard practice. Liberty ships carried 4 separate pumping systems with independent power sources and piping networks. Damage to any 2 systems still left capacity for managing flooding in damaged compartments. The approach added approximately 40 tons to ship weight, but created survivability margins that proved decisive under combat conditions. Electrical generation followed similar redundancy principles. In addition to the main turbine-driven generator providing ships power, Liberty ships carried 2 diesel generators and a battery-powered emergency system. The multiple power sources ensured that critical systems, including pumps, communications, and lighting, could continue operating despite damage that would leave conventionally designed vessels dead in the water. May 1943, Maritime Commission Engineering Offices. Gibbs reviewed preliminary data from Liberty ship operational experience with growing confidence that wartime casualties were validating design approaches that peacetime economics had discouraged. His technical staff compiled statistics showing that redundant systems substantially improved vessel survival under damage conditions that would sink conventional merchant ships. The analysis revealed specific scenarios where redundancy created survival margins. When torpedo explosions destroyed portions of the primary electrical system, backup generators maintained power for damage control operations. When flooding disabled main pumping equipment, secondary pumps prevented progressive water accumulation that could overwhelm vessel stability. Compartmentalization effects appeared equally significant. Torpedo hits that breached hull integrity created flooding limited to specific compartments rather than spreading throughout the vessel. The watertight bulkhead system contained damage, preventing the catastrophic flooding that had characterized merchant ship losses during the First World War. Technical specifications for Liberty ship construction had emphasized system separation to prevent single points of failure. Redundant equipment occupied different locations within the hull, ensuring that damage affecting one system wouldn't simultaneously disable its backup. The approach reflected lessons from naval architecture applied to merchant vessel design, treating combat damage as a design parameter rather than an operational contingency. Engineering calculations suggested that redundancy added approximately 12% to construction costs compared to minimum specification merchant vessels. The expense had created resistance during design approval processes, with budget officers questioning whether wartime resource constraints justified such apparent over-engineering. Casualty data provided conclusive justification, demonstrating that survival improvements more than offset additional construction investment. Henry Kaiser's production methods at Richmond and other West Coast shipyards had proven that redundant systems didn't necessarily slow construction. The prefabrication approach allowed parallel assembly of primary and backup equipment, with installation proceeding simultaneously rather than sequentially. Total construction time remained under 50 days despite system complexity that exceeded conventional merchant vessels. Quality control remained the critical challenge in high-speed construction. Welded hulls required careful inspection to prevent defects that could compromise watertight integrity. Torres and other welding supervisors maintained rigorous standards despite production pressures, understanding that minor flaws could prove fatal when vessels encountered combat damage. The welding technique itself represented controversial innovation. Traditional shipbuilding relied on riveted construction that provided mechanical flexibility, allowing hull plates to shift slightly under stress without creating crack propagation paths. Welded joints created rigid connections that could concentrate stress at weld points, potentially leading to catastrophic failure. Liberty ship specifications addressed welding concerns through careful material selection and fabrication procedures. Steel plates used low-carbon alloys that resisted brittle fracture, while welding sequences minimized thermal stress accumulation. The approach worked effectively in most conditions, though occasional failures demonstrated that welding technology still carried risks that riveting avoided. December 1942 had brought the first indication of welding problems, when 3 Liberty ships suffered hull fractures in cold North Atlantic waters. The SS John P. Gaines developed cracks extending 40 feet along deck seams, threatening structural integrity despite calm seas. Engineering investigation revealed that low temperatures reduced steel ductility, allowing stress concentrations at weld points to propagate into major fractures. The brittle fracture problem represented serious threat to Liberty ship reliability, potentially undermining the entire production program. Maritime Commission metallurgists worked urgently to understand failure mechanisms and develop solutions that could be implemented without disrupting construction schedules. The research revealed complex interactions between welding procedures, steel composition, and operating temperatures. Solutions emerged through modifications to steel specifications and welding techniques. Higher quality steel with improved low-temperature properties reduced fracture susceptibility, while revised welding sequences minimized residual stress. Additional structural reinforcement at stress concentration points prevented crack propagation even when minor flaws appeared. The brittle fracture issue highlighted tensions between rapid construction and engineering reliability. Kaiser's production methods achieved unprecedented building speeds, but created quality control challenges that traditional shipyards would have considered unacceptable. The compromise involved accepting occasional failures while implementing systematic improvements that reduced defect rates to acceptable levels. By mid-1943, welding procedures had evolved to minimize brittle fracture risks while maintaining construction velocities that kept pace with vessel losses. The learning process cost several ships and crews, but established fabrication standards that would influence post-war shipbuilding across the maritime industry. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. June 6, 1944. Normandy invasion required the largest amphibious operation in military history, with logistics depending critically on Liberty ship capacity to transport equipment and supplies across the English Channel. The redundant systems that Gibbs had specified 3 years earlier would face their ultimate test under conditions combining combat damage with operational demands that exceeded any previous merchant vessel employment. Liberty ships provided primary transportation for vehicles, ammunition, and fuel-supporting operations on the Normandy beaches. Each vessel carried cargo worth millions of dollars in military equipment, making survival after damage essential to maintaining supply flow. The invasion's success depended partly on whether merchant vessels could sustain operations despite German air attacks and coastal artillery that would inflict inevitable casualties. The SS Charles Morgan struck a mine off Utah Beach on June 7th, suffering hull damage that flooded one cargo hold and damaged primary pumping equipment. Redundant systems maintained vessel stability, while emergency repairs allowed continued unloading operations. The Morgan delivered 80% of her cargo before requiring towing to English repair facilities. Similar scenarios played out across dozens of Liberty ships during the first weeks of the Normandy campaign. Vessels absorbed damage from mines, artillery fire, and occasional air attacks, yet continued operations due to system redundancy that prevented single hits from causing mission failure. The operational tempo exceeded anything merchant vessels had previously sustained. Maritime Commission analysts documented Liberty ship performance during Normandy operations, with attention to how redundant systems translated into sustained cargo delivery under combat conditions. The data revealed that approximately 70% of Liberty ships sustaining moderate damage completed their primary missions, compared to 30% for conventionally designed merchant vessels in similar circumstances. The survival statistics validated engineering approaches that prioritized mission completion over minimal construction costs. Gibbs' redundant systems had created margins, allowing vessels to sustain damage while continuing operations essential to military success. The approach represented fundamental shift in merchant vessel design philosophy, treating combat damage as normal operating condition rather than catastrophic contingency. August 1944, Mediterranean convoy routes. The SS Samuel Parker survived 3 separate torpedo attacks during convoy UGS 47's transit from Norfolk to Naples, demonstrating Liberty ship survivability under sustained damage that would have sunk conventional merchant vessels multiple times over. The Parker's experience illustrated how redundant systems created compounding survival advantages when vessels faced repeated damage. The first torpedo struck at 0200 hours on August 12th, penetrating the hull near frame 48 and flooding cargo hold. Number 2. Primary pumping equipment in that section sustained damage from the explosion, but secondary pumps located in the adjacent compartment maintained water removal capacity. The Parker reduced speed to 8 knots but continued with the convoy. 14 hours later, a second torpedo hit near the stern, damaging rudder controls and disabling the main steering system. Emergency steering from the auxiliary rudder room allowed continued maneuvering, though directional control required constant attention from helmsmen, working manually operated backup controls that conventional merchant vessels typically lacked. The third attack came on August 14th, with a torpedo striking forward of the bridge structure. The explosion destroyed the main radio room and primary electrical generation equipment. Emergency generators, located in a protected stern compartment, maintained power for essential systems, while backup radio equipment allowed the Parker to maintain convoy communication. Captain William Schroeder reported that survival depended entirely on redundant systems that conventional naval architecture would have considered unnecessary expense. Each torpedo hit disabled primary systems, but backup equipment allowed continued operations that kept the Parker moving toward her destination. The vessel reached Naples under her own power, delivered 60% of her cargo, and sailed to Palermo for repairs. Maritime Commission engineering staff analyzed the Parker incident with particular attention to how multiple system failures interacted. The casualty report documented that no single redundant system proved decisive. Rather, the combination of backup pumps, emergency steering, auxiliary power generation, and compartmentalization created survival margins that accumulated with each damage incident. Statistical analysis revealed patterns invisible to individual casualty reports. Liberty ships experiencing multiple damage incidents showed substantially higher survival rates than conventional merchant vessels facing similar circumstances. The redundancy philosophy created what engineers termed defense in depth, where secondary and tertiary backup systems provided protection when primary and first-level backups failed. William Francis Gibbs reviewed these reports with professional validation. His career had been spent advocating engineering approaches that prioritized reliability through redundancy rather than minimizing construction costs. The wartime experience demonstrated that apparently wasteful over-engineering became essential capability when operating conditions exceeded peacetime planning assumptions. The mathematical relationship between redundancy and survivability followed probability principles that Gibbs had understood intuitively, but could now validate empirically. If any critical system had 90% reliability under damage conditions, a single backup raised effective reliability to 99%, while 2 backups approached 99.9%. The compounding effect meant that modest additional investment in redundant systems produced disproportionate improvements in mission completion probability. September 1944, Kaiser Richmond Shipyard No. 3. Production supervisor Margaret Wilson walked the assembly floor where hull sections for the SS Robert E. Peary were being welded in a construction process that had become almost routine despite its revolutionary departure from traditional shipbuilding. The yard had completed 263 Liberty ships since operations began in December 1941, with average construction time now under 45 days from keel laying to launch. Wilson's clipboard held quality control checklists that emphasized weld integrity and system installation verification. Each Liberty ship required approximately 300 to 30 miles of welding, creating potential failure points that could compromise the redundant systems on which survival depended. Quality control represented the essential link between Gibbs' design philosophy and operational reliability. Welding inspector James Kowalski examined frame 62 welds, where hull plates joined structural members that carried stress loads during combat damage. His hammer test revealed a hollow sound, indicating subsurface void in the weld material. The defect required grinding out the affected section and rewelding, adding approximately 4 hours to construction schedule, but ensuring structural integrity that might prove decisive if the vessel encountered torpedo attack. The tension between speed and quality persisted throughout Liberty ship production. Kaiser's revolutionary methods achieved construction velocities that traditional shipyards considered impossible, but rapid fabrication created quality control challenges. Wilson's inspection protocols represented compromise between production tempo and reliability standards that distinguished functional vessels from floating coffins. Technical specifications for redundant system installation required particular attention to physical separation. Backup pumps needed placement in compartments remote from primary equipment, ensuring that single torpedo hits wouldn't simultaneously disable both systems. Emergency generators required protection from magazine explosions that might destroy main power generation. The spatial distribution added complexity to construction sequencing. Electrical systems demonstrated the practical challenges of implementing redundancy in high-speed construction. Liberty ships carried 4 separate electrical distribution networks, each capable of maintaining essential services independently. The wiring harnesses required careful routing through different compartments, with junction boxes protected from fragment damage and flooding. Installation consumed approximately 200 man-hours per vessel. Pumping system redundancy followed. Similar principles with additional mechanical complexity. Each Liberty ship mounted 4 separate pump sets capable of removing water from damaged compartments. The pumps drew power from different electrical systems and discharged through independent piping networks. Damage to any 2 systems still left capacity exceeding minimum requirements for damage control. The redundant steering systems that saved the Samuel Parker required mechanical backup controls physically separated from primary hydraulic systems. Emergency steering from the auxiliary rudder room used manual gear reduction that allowed helmsmen to control rudder position without electrical or hydraulic power. The system represented 19th century technology maintained as essential backup to modern controls. Fire suppression capabilities exceeded standard merchant vessel specifications through redundant water distribution systems and backup firefighting equipment. Liberty ships carried portable pumps that could be deployed if fixed systems sustained damage, along with emergency water supplies in protected tanks. The approach reflected lessons from merchant vessel losses, where initial damage proved survivable, but subsequent fires caused vessel destruction. October through December 1944, North Atlantic and Pacific convoy routes. Liberty ship operational experience accumulated into statistical datasets that allowed systematic analysis of how design features influenced survival under various damage scenarios. Maritime Commission engineering staff compiled casualty reports covering nearly 600 separate damage incidents, creating empirical foundation for understanding redundancy effectiveness. The analysis revealed that compartmentalization provided the most significant survival advantage, preventing progressive flooding that conventional hull designs couldn't contain. Liberty ships, with 3 flooded compartments, showed 75% survival rate compared to 30. 5% for traditionally constructed merchant vessels with similar damage. The watertight bulkhead system represented Gibbs' most important single design innovation. Redundant pumping systems ranked second in survival impact, maintaining damage control capability when primary equipment sustained combat damage. Vessels equipped with backup pumps showed 60% higher probability of controlling flooding compared to ships relying on single pump systems. The relatively modest additional cost of secondary pumping equipment produced disproportionate survival improvements. Emergency power generation contributed substantially to mission completion rates even when vessels sustained damage, preventing return to port. Liberty ships, maintaining electrical power, could operate communications, navigation, and damage control equipment that allowed continued operations despite structural damage. The capability proved especially valuable during complex operations like Normandy, where damaged vessels needed completion of cargo discharge before seeking repairs. Naval architect David Richardson reviewed the statistical analysis with growing appreciation for design philosophy that prioritized mission completion over construction economy. The redundancy that critics had called wasteful was proving essential to sustaining merchant vessel operations under wartime conditions. Richardson's post-war career would involve applying these lessons to commercial shipbuilding, though peacetime economics would limit implementation. The material cost of redundancy appeared modest when measured against operational benefits. Additional pumping systems added approximately $15,000 to construction costs, averaging $300,000 per vessel. Emergency generators contributed another $8,000. Improved compartmentalization required minimal additional expense beyond design complexity. Total redundancy costs represented roughly 8% construction premium. Against these costs, the Maritime Commission weighed survival benefits measured in vessels saved and cargo delivered. Liberty ships showed approximately 35% higher survival rates following torpedo attacks compared to conventional merchant vessels. The improvement represented dozens of vessels saved along with crews and cargo that otherwise would have been lost. Economic analysis suggested that redundancy paid for itself through reduced vessel losses. Each Liberty ship saved represented $300,000 in construction costs avoided, plus cargo value that often exceeded vessel value. The mathematics indicated that redundancy investment achieved positive return, even ignoring human lives saved, though that calculation seemed obscene to analysts who understood that statistics represented real crews who returned home to families. January 1945. Maritime Commission Strategic Planning Offices. The war's approaching conclusion allowed reflection on shipbuilding programs that had sustained Allied logistics throughout the conflict. Liberty ship production would total approximately 2,700 vessels by war's end, the largest single class of ships built to common design in maritime history. The program's success owed much to revolutionary construction methods, but also to engineering philosophy that prioritized survivability through redundancy. William Francis Gibbs found himself reviewing his design decisions from 3 years earlier with satisfaction that vindicated career-long advocacy for redundant systems. The EC-2SC-1 specifications had incorporated features that peacetime naval architecture would have rejected as over-engineered, but wartime experience demonstrated that apparent excess became essential capability under combat conditions. His design philosophy reflected fundamental understanding that engineering specifications should account for operating conditions, including catastrophic failures. Redundant systems represented insurance against scenarios that probability suggested would occur rarely, but consequences demanded must be survived. The approach contradicted peacetime economics that optimized for normal operations while accepting occasional catastrophic losses. The broader implications extended beyond ship design into questions about how engineering should balance construction economy against operational reliability. Liberty ship experience suggested that modest additional investment in redundant systems could produce disproportionate improvements in mission success probability. The lesson applied across domains from aircraft design to electrical power distribution. Technical analysis documented specific mechanisms through which redundancy translated into survivability. Physical separation prevented single damage events from disabling primary and backup systems simultaneously. Diverse technology bases meant that failure mechanisms affecting one system wouldn't necessarily impact backups operating on different principles. Standardized interfaces allowed damaged primary systems to be bypassed in favor of backup equipment without requiring extensive reconfiguration. The redundancy principles that proved effective in Liberty ships influenced post-war commercial shipbuilding, though economic constraints limited implementation compared to wartime standards. Passenger vessels adopted multiple power generation systems and improved compartmentalization that reflected lessons from combat damage analysis. Tankers incorporated redundant pumping systems that could manage emergency situations without depending on single critical equipment. Military shipbuilding embraced redundancy as fundamental design requirement, with specifications mandating backup systems for all critical functions. Naval architects designing destroyers and aircraft carriers applied Liberty ship lessons about physical separation and diverse technology to create vessels that could survive battle damage that would have destroyed earlier warships. The carrier, USS Forrestal, incorporated Gibbs principles throughout her design, with redundant systems that saved the vessel during catastrophic flight deck fire in 1967. The psychological impact on merchant marine crews proved as significant as technical survivability improvements. Sailors serving aboard Liberty ships understood that redundant systems provided protection beyond what conventional merchant vessels offered. The knowledge influenced morale and retention in dangerous occupation, where merchant marine casualties exceeded most military services during the war's peak years. Captain Raymond Miller, who commanded 4 different Liberty ships during Atlantic convoy operations, described the confidence that redundant systems provided during combat damage situations. Knowing that backup equipment existed created different mindset compared to conventional vessels where system failure meant immediate crisis, he explained during post-war interviews. The redundancy provided time to assess damage and implement repairs rather than abandoning ship at first indication of trouble. March through May 1945, Pacific Theater operations. Liberty ships supported final campaigns against Japanese positions across the Western Pacific, sustaining damage from kamikaze attacks that represented different threat profile than Atlantic torpedo warfare. The redundancy designed for underwater hull damage proved equally valuable against aerial attack that could destroy superstructure systems while leaving hull integrity intact. The SS Matthew P. Dede survived kamikaze impact that destroyed the bridge structure and killed 12 crew members, including the captain. Emergency steering from the auxiliary rudder room allowed continued maneuvering, while backup communications equipment maintained contact with convoy escorts. The Dede completed her mission delivering supplies to Okinawa before returning to Guam for repairs. Casualty analysis from Pacific operations validated redundancy principles under different damage scenarios than originally anticipated. Gibbs had designed backup systems primarily for torpedo damage, affecting hull integrity and machinery spaces. Kamikaze attacks often destroyed superstructure while leaving engineering plants functional, creating situations where redundant steering and communications proved more critical than backup pumping capacity. The adaptability demonstrated Liberty ship robustness across threat environments that differed substantially from design assumptions. Redundant systems provided survival margins regardless of specific damage mechanisms, suggesting that defense in depth through multiple backup capabilities created general resilience rather than protection against particular threats. Statistical comparison between Liberty ships and conventional merchant vessels in Pacific operations showed similar survival advantages as Atlantic theater data. Liberty ships sustaining kamikaze damage showed 40% higher probability of mission completion compared to traditionally designed vessels with comparable damage. The improvement represented direct consequence of redundant systems that Gibbs had specified based on Atlantic convoy requirements. June 1945, Kaiser Richmond Shipyard. The final Liberty ship, the SS Albert M. Bow, launched on September 27, closing production program that had built 2,710 vessels in under 4 years. The achievement represented triumph of mass production applied to complex engineering, but also validation of design philosophy that prioritized reliability through redundancy, despite construction cost implications. Henry Kaiser's revolutionary fabrication methods had proven that redundant systems didn't necessarily slow production or dramatically increase costs. Prefabrication allowed parallel assembly of primary and backup equipment, with installation proceeding simultaneously rather than sequentially. The approach demonstrated that engineering reliability and construction velocity could coexist when manufacturing processes adapted to design requirements. The final production statistics documented program scale that exceeded all previous shipbuilding efforts. Richmond and other yards had consumed approximately 7 million tons of steel, employed over 600,000 workers at peak production, and created vessels that transported roughly 70% of military cargo reaching overseas theaters. The logistics achievement would have been impossible without Liberty ship reliability that allowed vessels to sustain damage while completing missions. William Francis Gibbs received formal recognition from the Maritime Commission for engineering contributions that had measurably improved Allied logistics effectiveness. The citation acknowledged that redundant systems specified in EC2SC1 design had contributed to vessel survival rates substantially exceeding planning assumptions, thereby enhancing cargo delivery reliability essential to military operations. The recognition meant less to Gibbs than empirical validation that engineering philosophy emphasizing redundancy produced measurable operational advantages. His career satisfaction derived from seeing theoretical principles confirmed through wartime experience that provided natural experiments impossible to conduct during peacetime operations. August 1945, Worldwide Merchant Marine Operations. The war's conclusion allowed comprehensive analysis of Liberty ship performance across 44 months of sustained combat operations in Atlantic, Pacific, Mediterranean, and Arctic theaters. Maritime Commission statistical staff compiled final casualty data covering approximately 800 damage incidents, ranging from minor to catastrophic. The analysis confirmed that redundant systems substantially improved survival probability across all damage categories. Liberty ships showed 38% higher survival rate following major damage compared to conventional merchant vessels with similar displacement and cargo capacity. The improvement represented approximately 200 vessels and 4,000 crew members who survived incidents that would have proved fatal aboard traditionally designed ships. Compartmentalization effects dominated survival statistics, preventing progressive flooding that characterized merchant vessel losses during earlier conflicts. Liberty ships could survive flooding in any 3 adjacent compartments, providing margins that allowed damage control even after catastrophic torpedo hits. The watertight bulkhead system represented single most important survival feature. Redundant pumping capacity ranked second in survival impact, allowing continued water removal when primary systems sustained damage. Vessels maintaining pumping capability showed 70%. Mission completion rate despite major flooding, compared to 20% for ships losing pump capacity. The relatively modest cost of backup pumps produced disproportionate survival improvements. Emergency power generation contributed substantially to mission success, even when vessels couldn't return to port under their own power. Liberty ships maintaining electrical supply could operate communications and navigation equipment, allowing coordination with rescue vessels or towing to friendly ports. The capability proved especially valuable in Arctic convoys, where cold water temperatures made crew survival dependent on maintaining power for heating systems. The mathematical relationship between redundancy, investment, and survival improvement suggested optimal design parameters for future merchant vessel construction. Analysis indicated that 2 levels of backup for critical systems provided maximum return on investment, with additional redundancy showing diminishing benefits. The finding influenced post-war commercial shipbuilding standards that incorporated selective redundancy for essential functions. September through December 1945, post-war transition. Liberty ships began conversion to peacetime merchant service, with military equipment removed and cargo handling capabilities modified for commercial operations. Many vessels continued service for decades, demonstrating that rapid wartime construction could produce durable ships when engineering design prioritized reliability through redundancy and quality control maintained fabrication standards. The SS Jeremiah O'Brien remained operational into the 21st century, serving as museum ship that demonstrated Liberty ship design principles to new generations of naval architects and maritime historians. Her survival represented testimony to engineering philosophy that viewed redundancy as investment in reliability rather than wasteful over-specification. William Francis Gibbs continued his career in naval architecture, designing the SS United States that incorporated redundancy principles validated by Liberty ship experience. His approach influenced commercial and military vessel design for decades, establishing engineering standards that treated system backup as essential capability rather than optional feature. The broader legacy extended beyond shipbuilding into engineering philosophy applicable across technical domains. Liberty ship experience demonstrated that modest investment in redundant systems could produce disproportionate improvements in reliability when operating conditions included possibility of catastrophic failures. The lesson influenced aircraft design, electrical power distribution, computer systems, and any domain where mission completion, despite component failures, justified additional design complexity. Modern reliability engineering traces intellectual lineage to wartime operational research that analyzed Liberty ship performance under combat conditions. The mathematical frameworks developed for understanding redundancy effectiveness evolved into formal methods, including fault tree analysis and failure modes and effects analysis, that guide contemporary engineering practice across industries. The final accounting showed that Liberty ship program had achieved objectives exceeding initial specifications. Vessels designed for 5-year service life continued operations for decades. Ships expected to face occasional torpedo attacks survived sustained combat damage across multiple theaters. Redundant systems that critics called wasteful proved essential to Allied logistics success. In quiet moments after the war, William Francis Gibbs reflected on design decisions made under pressure when German submarines threatened to sever Allied supply lines. The redundancy, he specified, had seemed excessive to critics focused on construction economy, but wartime experience vindicated engineering philosophy that prioritized mission completion over minimal costs. The mathematical precision of his redundancy calculations had translated into thousands of crew members who returned home rather than becoming casualty statistics. Each backup pump, emergency generator, and watertight bulkhead represented lives saved through engineering discipline that anticipated catastrophic failures and designed systems that could survive them. The SS Richard Hovey, the vessel that opened this story, completed repairs in Iceland and returned to convoy service. She survived 2 additional torpedo attacks before war's end, each time remaining afloat long enough for crew rescue and partial salvage. Her survival demonstrated that engineering redundancy created margins, allowing vessels to sustain damage that conventional naval architecture considered fatal. The Liberty ships represented more than emergency shipbuilding program or logistical achievement. They embodied engineering philosophy that understood reliability required redundancy, that backup systems justified their cost through catastrophic failures prevented rather than normal operations optimized. The principle transcended specific application in wartime merchant vessels to influence how engineers approach design challenges across every domain where failure consequences demanded prevention rather than acceptance. In the 7 decades since Liberty ships crossed submarine-infested waters carrying cargo essential to Allied victory, their engineering legacy has influenced countless systems where redundancy provides margins between success and catastrophic failure. Modern aircraft carry multiple hydraulic systems, backup flight controls, and redundant electrical generation that reflect principles Gibbs applied to merchant vessel design. Nuclear power plants incorporate defense in depth through multiple safety systems operating on diverse principles. Computer data centers maintain redundant power supplies, cooling systems, and network connections that ensure continued operation despite equipment failures. The lesson remains timeless. Redundancy that appears wasteful during normal operations becomes essential capability when systems face conditions exceeding design assumptions. The modest additional investment in backup capabilities produces disproportionate improvements in reliability measured across system lifetime rather than initial construction costs. William Francis Gibbs understood this intuitively, but Liberty Ship wartime experience provided empirical validation that influenced engineering practice for generations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.